Hey there. Ready to unlock the secrets of the stars? You sent us some really cool stuff about stars, and we're going to unpack all of it, diving deep into how they work,
Yeah.
where they come from, and ultimately how they meet their end. Think of this as your all-access pass to the stellar evolution show. From the dramatic birth in vast nebulae to the mind-blowing finale.
And what's fascinating is that even though we see stars every night, twinkling away, their lifespans are so incredibly long,
Hmm,
and the scales are so massive that it's hard to grasp just how dynamic they truly are.
that's true. Like one of your articles mentioned that some red dwarf stars may even outlive the eventual heat death of the universe. That's a level of longevity we can hardly fathom. But let's rewind to the beginning, to the cosmic cradles where stars are born. I'm talking about nebulae, these massive clouds of gas and dust scattered throughout the universe.
Yes, these nebulae are like stellar nurseries. They're stunningly beautiful, and it's gravity that kicks off the entire star-forming process. It acts like a sculptor, slowly pulling in gas and dust, compressing it into these dense clumps called protostars.
One of your sources had a great analogy, described this balance like a balloon, where the air pressure inside is pushing out against the rubber, just like fusion energy pushes against gravity in a star. So it's not some instantaneous burst of light. It's more like a slow-motion cosmic dance,
Yeah.
with gravity orchestrating the whole thing, right? But your research paper mentioned this process taking millions of years. Why does it take so long for a star to form?
It's because the scales are just so enormous. And
Hmm.
gravity, while powerful on these scales, takes time to draw all that material together. As the protostar pulls in more and more material, the core gets incredibly dense and hot, millions of degrees hot. And at a crucial point, when the pressure and temperature in the core reach a tipping point, nuclear fusion
It's
ignites.
like flipping on a cosmic light switch.
It's more like slowly turning up a dimmer switch. The fusion process, where hydrogen atoms are forced together to form helium, releases a tremendous amount of energy. This outward pressure finally counteracts the inward pull of gravity, and the star enters a state of equilibrium.
That's what's called hydrostatic equilibrium, right? Given the immense forces at play. How often does this delicate balance go awry? Do you see examples of stars where this equilibrium fails?
That's a great question. And yes, we do observe stars that become unstable, either due to fluctuations in their internal processes or external factors. But for the vast majority of a star's life, this equilibrium holds, allowing it to shine steadily for millions, even billions of years. This stable phase is what we call the main sequence, and it's where stars spend most of their lives.
Our own sun is a main sequence star, right? But one thing that struck me from your research is just how much the lifespan of a star varies depending on its mass.
Absolutely. Our sun is about halfway through its main sequence lifetime, which is estimated to be around 10 billion years. But those tiny red dwarf stars, the ones we talked about earlier, can live for trillions of years because they burn their fuel so slowly. It's like comparing a bonfire that burns brightly and quickly to a slow-burning ember that lasts for ages.
So eventually, regardless of size, all stars run out of fuel. What happens when a star's fuel tank starts running low?
Well, it really depends on the star's initial mass. Let's start with low to medium mass stars like our sun. As they start to run out of hydrogen, they go through a sort of midlife crisis. They expand dramatically into what we call red
It's like
giants.
they're trying to grab onto their youth, puffing themselves up to appear larger than life.
That's a great way to put it. Inside the core, helium starts fusing into heavier elements as the star desperately tries to keep the energy flowing. This is a critical transition point in a star's life.
This is a gradual process?
Yeah.
Or is it more of a sudden shift?
It's a gradual process that takes place over millions of years. But for massive stars, things are much more dramatic and fast-paced.
All right, let's talk about those massive stars. How is their fuel crisis different?
Massive stars live fast and die young, in a cosmic sense anyway. They go through a similar red giant phase, but on a much grander scale, swelling into supergiants. And their cores are so hot and dense that they can fuse heavier elements, creating elements all the way up to iron.
And iron is the end of the line, right? I remember that from one of my astronomy classes. Why is that?
It's because fusing iron doesn't release energy. It actually requires it. Think of it like trying to squeeze energy out of a rock. You can put a lot of effort in, but you won't get much back. So when a massive star's core is filled with iron, it's like hitting a cosmic brick wall. Fusion stops, and there's no longer enough outward pressure to counterbalance the immense gravity.
So what happens next? Does the star just fizzle out?
Not exactly. What follows is one of the most spectacular events in the universe, a supernova. Without fusion to support it, The star's core collapses in on itself with incredible force. This collapse triggers a shockwave that tears through the star, blasting its outer layers into space with incredible speed and energy. Supernovae are so bright that they can outshine entire galaxies for a short period of time.
Wow, that's quite a dramatic ending. So we've got these supernovae for the massive stars and these slowly fading red giants for the smaller ones. What happens to the core after a supernova? Does it just disappear?
Not at all. What's left behind depends on the original mass of the star. For smaller stars like our sun, the core becomes a white dwarf, a dense, Earth-sized object that slowly cools over billions of years.
So it's like a cosmic ember fading into the darkness.
That's a good analogy. But for those massive stars that go supernova, the core's fate is even more bizarre, depending on the mass. It can either become a neutron star or a black hole.
Okay, let's talk about those. Neutron stars sound pretty intense.
They are incredibly extreme. Imagine squeezing the entire mass of the sun into a city-sized ball. That's the kind of density we're talking about. A teaspoonful of neutron star material would weigh billions of tons on Earth.
That's mind-boggling.
Mhm.
And then there are the infamous black holes.
Black holes are regions of space-time where gravity is so strong that not even light can escape. They are the ultimate cosmic enigmas, warping space and time around them.
So they're kind of like cosmic vacuum cleaners, sucking up anything that gets too close.
That's a simplified way to think about it. But their gravity is so intense that they warp the fabric of space-time itself.
So we've covered the birth life and dramatic deaths of stars, but we haven't even touched on how they create the elements that make up everything around us. It's not just about light and heat, is it?
Not at all. Stars are truly the alchemists of the universe, forging heavier elements from lighter ones.
Okay, so let's unpack that a little bit. How do stars actually create these elements?
It all comes down to nuclear fusion, the process happening at the core of stars. During their main sequence lives, stars primarily fuse hydrogen into helium. But as they evolve, and particularly during those dramatic supernova events, the temperatures and pressures inside become so extreme that heavier elements are created, all the way up to iron.
So is that where the gold in my ring came from? A
Yeah.
supernova explosion.
Exactly. And the carbon in your body,
Yeah.
the oxygen you breathe, the silicon in your computer, all of these elements were forged in the heart of stars. We are, quite literally, made of stardust. It's one of the most mind-blowing concepts in astronomy. We are connected to the cosmos in the most fundamental way imaginable.
It makes you look at the night sky in a whole new light, that's for sure. But speaking of the bigger picture, you know what else blew my mind from your research? It's not just about the elements themselves. It's about how stars shape galaxies, how they influence the formation of planetary systems. I mean, it's a whole cosmic web of connections.
Exactly. It's like a giant cosmic ecosystem. Let's zoom out for a second and consider galaxies. Stars are the fundamental building blocks of galaxies. Their combined gravity holds these vast structures together, shaping their spiral arms, their central bulges, their entire dynamic form. One of your articles had a great visualization. It showed how the distribution of stars within a galaxy and the way they orbit the galactic center is directly related to the galaxy's overall shape and how it evolves over time.
So a galaxy isn't just a random scattering of stars. There's a complex interplay between them, all orchestrated by gravity.
Precisely. And as stars are born and die, they inject energy and matter back into the interstellar medium sea. That's the gas and dust that fills the space between stars. This constant cycle of stellar birth, life, and death drives the evolution of galaxies over billions of years.
And this brings us to planetary systems, right? I mean, our own solar system is a testament to how a star can influence the formation of planets. How does that process actually work?
We'll think back to those stellar nurseries we talked about. When a star forms, it's usually surrounded by a disk of leftover gas and dust. The star's gravity acts like a shepherd, pulling this material together. Over millions of years, these particles clump together, forming larger and larger bodies. Eventually, planets emerge from this swirling disk.
So stars are like the cosmic architects, setting the stage for the creation of planets. But you mentioned that a star's characteristics can also affect the kinds of planets that form. Can you elaborate on that a bit?
Absolutely. A star's mass, temperature, and luminosity play a huge role in determining the conditions within its planetary system.
Yeah.
For example, planets forming closer to a hotter star will be much hotter than those forming farther away. This affects whether a planet is likely to be a gas giant like Jupiter or a rocky world like Earth.
So it's like cosmic real estate.
It's a location.
Location, right? It's amazing how a star's properties can influence whether a planet can support liquid water, an atmosphere, and potentially even life.
It is truly remarkable. And as stars evolve, They can continue to influence the fate of their planetary systems. One of your sources, a research paper on stellar evolution, talked about how the habitable zone around a star actually shifts over time as the star gets older and brighter. That zone moves outward, which could have major implications for any planets orbiting within it.
That's fascinating. So
Yeah.
even planets that might not be habitable today could become so in the future as their host star evolves.
Exactly. And conversely, planets that are currently in a habitable zone might eventually become too hot as their star expands. It's a dynamic process that highlights the intricate relationship between stars and their planetary companions.
So we've journeyed from the birth of stars in these vast nebulae through their lives as cosmic furnaces to their dramatic deaths as supernovae or their gradual fading as white dwarfs. We've talked about how they create the elements that build our universe and how they shape galaxies and influence planetary systems. But this incredible story doesn't end there, does it? I mean, if stars are constantly being born and dying, what does that mean for the universe as a whole? Where does this all lead?
That's one of the biggest questions astronomers are grappling with. What is the ultimate fate of the universe?
It's almost too big to wrap your head around.
Yeah.
But your sources mentioned a few interesting possibilities, right?
Yes. The universe is constantly expanding, and the big question is whether that expansion will continue forever, or eventually slow down in reverse if it keeps expanding. We're looking at a scenario called the Big Freeze. As the universe expands, everything gets more spread out, and things cool down. Eventually, stars will burn out, galaxies will drift farther apart, and the universe will become a cold, dark, and incredibly empty place.
That's kind of a bleak picture, to be honest. But there are other possibilities too, right? What about this big crunch idea?
The Big Crunch is the opposite scenario. If the expansion slows down enough, and gravity eventually wins the cosmic tug of war, the universe could start contracting. Everything would get closer and closer together, eventually collapsing in on itself in a fiery, dense singularity.
Sounds like rewinding the Big Bang. Are those the only two possibilities?
There are other more exotic theories as well, like the Big Rip scenario, where the expansion accelerates so rapidly that it eventually tears apart galaxies, stars, and even atoms themselves. But currently, the most widely accepted idea is that the universe will continue to expand, heading towards that eventual big freeze.
Well, that gives us plenty of time to keep exploring. But before we get lost in these mind-boggling scenarios, billions of years in the future, let's bring it back to our own little corner of the universe. What about the future of our own star, the sun? We know it's a main sequence star, but eventually, it's going to run out of fuel too, right?
Absolutely. In about 5 billion years, the sun will start to run low on hydrogen fuel and enter its red giant phase.
Okay, so rewind back to what we talked about earlier. The sun is going to swell up, engulfing the inner planets. Does that include Earth? I'm assuming that doesn't bode well for us.
It's not looking good for Earth, to be honest. As the sun expands, its outer layers will reach out beyond Earth's current orbit. Whether Earth is completely swallowed up or just scorched to a crisp is still being debated.
Well, that gives us a few billion years to work on our interstellar travel plans.
Yeah.
But in all seriousness, what happens after the sun's red giant phase? Does it just fizzle out?
After the red giant phase, the sun will shed its outer layers, creating a beautiful planetary nebula, much like the ones we see scattered throughout the galaxy. The sun's core will contract, becoming a white dwarf, a dense, Earth-sized object that will slowly cool over billions of years.
So our sun, the source of all life and energy on Earth, will eventually end its life as a cooling ember, slowly fading into the cosmic background. It's kind of a poetic end to an incredible journey.
It really puts things in perspective, doesn't it? Our sun, which seems so permanent and unchanging, is just one player in this vast cosmic drama. And its story, like the stories of all stars, is a reminder of the interconnectedness of everything in the universe.
It really makes you appreciate the vastness of time and space, doesn't it? But, yeah. One of your articles mentioned something really interesting about how even though stars die, their deaths contribute to the birth of new stars. It's like a cosmic recycling program.
Exactly. When a star dies, especially in a supernova, it blasts out all those heavy elements that it forged during its lifetime, scattering them across the galaxy. Those elements become part of the interstellar medium, the gas and dust that fill the space between stars.
So that material doesn't just disappear. It becomes the building blocks for future generations of stars and planets.
Precisely. Those enriched clouds of gas and dust eventually collapse under gravity, forming new stars. And the cycle begins anew. It's a beautiful and continuous process of cosmic creation and renewal.
It makes you wonder what future generations of stars will look like, right? I mean, if they're forming from material enriched by previous generations, does that mean they'll be different in some way?
That's a great question. And yes, it's likely that stars born from material enriched by supernovae will have a slightly different chemical composition than older stars. They'll have a higher abundance of those heavy elements, which could influence their evolution,
Hmm.
their lifespan, and even their ability to form planetary
So if
systems.
the cosmos is constantly evolving, becoming more and more complex over time.
That's the beauty of it. It's not a static system. It's a dynamic, ever-changing tapestry woven from the lives and deaths of countless stars.
We've covered so much ground today, from the birth of stars and those stunning nebulae, to their incredible lives as cosmic furnaces,
Mm.
to their mind-blowing death as supernovae, or their gradual fading as white dwarfs. We've talked about how they create the elements that make up everything around us, how they shape galaxies, and how they influence the formation of planetary systems. But before we wrap up, I have one final question,
Mm.
and it's a big one.
I have a feeling I know where this is going.
Okay, so we talked about the eventual fate of the sun. But what about the ultimate fate of the universe? I mean, billions, even trillions of years from now. What's the grand finale? Do we have any clues?
It's one of the most profound and challenging questions in all of science. And as we discussed earlier, there are a few leading theories. The ultimate fate of the universe likely depends on a delicate balance between the outward push of expansion and the inward pull of gravity, the big freeze, where the universe expands forever, becoming cold and dark. Seems like the most likely scenario based on current observations.
So slow fading into darkness. It's a bit melancholic, but also kind of peaceful in a way.
It's a reminder of the vastness of time and the impermanence of everything, even the universe itself. But who knows? Maybe there are surprises in store for us after all. Every new discovery in astrophysics seems to unveil even more mysteries.
That's what makes it so exciting. So for you listening out there, the next time you look up at the night sky, try to see beyond those twinkling points of light. Imagine the incredible processes happening within each star, the elements being forged, the planets that might be orbiting, the vast cosmic dance of creation and destruction playing out on a scale that's almost impossible to grasp.
And remember, you are a part of this story. The very atoms that make up your body were created in the hearts of stars. We are all connected to the cosmos in the most fundamental way imaginable.
Keep looking up, keep asking questions,
Mm-hmm.
and keep exploring. The universe is full of wonders waiting to be discovered. That's it for our deep dive into the secret life of stars. We hope you enjoyed the journey.